Introduction. The Collatz Conjecture. It will be explained in detail. Explain step by step. And, I will also show you the solution to this problem. Let me explain to you the Collatz problem. In modular arithmetic notation, we can define the function f as follows. Consider the following operation, on an arbitrary positive integer. If the number is even, simply divide it by 2. If the number is odd, triple it and add 1. Select an integer type number. If you have chosen an even number, divide it by 2 and continue. Now if the result is odd, or you started with an odd number, multiply it by 3 and add 1. From the resulting even number, divide by 2 to get a new number. If you keep repeating this operation, it seems that you always eventually get to 1, no matter what odd or even number you started with. Is that true? Well, that is what we are going to find out. Let us see an example. Imagine, you chose the number 12. 12 is an even number, therefore we divide it by 2. The result is 6, also an even number. So we divide by 2 again. 3 is an odd number, so multiply it by 3 and add 1. As before with even numbers, we divide by 2. Let's move the number to have more space. Remember that we shouldn't stop until we get to 1. 8 divided by 2 is 4. And 4 divided by 2 equals 2. Finally, we come to the last division, which ends in 1. We can see that if you start with number 12, you end up with 1. In the first 2 minutes I introduced you to the Collatz conjecture, explained it, and showed it with an example. Remember, we need to find out if all the numbers reach 1 at the end. We will first find a frame where all the numbers will exist, and its inclusion will help us arrive at an answer. It is clearly easy to see that starting with the number 4 will take us to 1. This is still true if we multiply the top number in the list by 2. This will continue to infinity. Let's build groups based on this. The loop group is unique and interesting. You will easily see that all 4 numbers end up in an endless loop. Number 3 is included, even if it's the only one jumping out of the group. The numbers included are 5, 6, 7 and 8. The value below corresponds to the value of the number after the corresponding operation. Let me explain the meaning of the red arrow. The next value of the number, in this case 5, is 16, but 16 will be divided by 2, which is 8. And 8 is a member of this group. Let me talk about the green arrow. In this example, take the number 7. 7 multiplied by 3 plus 1 is 22 and 22 divided by 2 is 11. A green arrow indicates number 11 is part of the next group. The blue arrow describes a new value contained in the previous group. Now that I've explained the meaning of the arrows, let's move on. Our group 2 consists of the numbers 9 to 16. In blue is the value of the number for the next step. Note that each new group has twice as many numbers included in the group. Accordingly, group 3 and each group thereafter are constructed in the same way. There are many details worth mentioning, but I'll come back to them later. As I said before, we could form infinitely many groups. To confirm that, we will find out the position of number 141 without having the group in front of us. Because we're working with groups in base 2, we'll start with 2 squared. Increase the exponent until the expression is greater than 141. 2 to the power of 3 equals 8, and 8 is less than 141. 2 to the power of 4 is 16 and 16 is less than 141. 2 to the power of 5 is 32 and 32 is also less than 141. Let's jump to 2 to the power of 7, it is 128 and 128 is still less than 141. Finally, 2 to the power of 8 is 256, and 256 is greater than 141. First subtract 141 from 256. Lower the exponent from 8 to 7. Now subtract 115 from 128. There you have it, the position of number 141 is 13 in a group of 128 numbers. As you can see, it is possible to find any number and its position. It's also possible to find the corresponding color of the arrow, but I'll show that another time. We've selected a frame to work on. We know how to build infinite groups. And we learned how to find the position of a number. You've probably seen this type of tree. They're nice but not useful. Please take the time to understand the distribution of the numbers. The numbers grow to infinity on both the x-axis and the y-axis. The red dot indicates there is no odd number multiplied by 3 plus 1 gives that number. If you create a list containing only the blue numbers, no number will be missing or repeated. Let's go back to the beginning. Notice that the numbers on both axes grow by the same factor. In simple words, it's not a conjecture, it's a fact. Each number will come back to 1. Let me show you some interesting facts and details. Do you remember our second group? Let's look at it again. And add some numbers of the next group. In reality, we can forget about multiplying and just use addition and subtraction. Pay attention to the selected numbers. If we have an odd number, say the number 11, all we have to do is add half of the next number to our number, and we get the new position. Remember that 34 divided by 2 is 17. Now let's add some numbers from the previous group. This time, starting with number 12, we need to subtract half of its own value. This applies to any pair of numbers. Note that the odd number must be less than the even number. The value you add or subtract is the same for both operations.